Hello there, and welcome to The Sleepy Scholar. Tonight's journey takes us into 100 sleepy facts about caves, where quiet passages, mineral curtains, hidden rivers, dark chambers, and ancient traces all become part of one slow underground story. We will follow water through stone, listen to the silence of deep rooms, and notice how caves shelter life, memory, and time beneath the surface. If you enjoy these calm explorations, consider subscribing so you can easily return here whenever you need to rest. For now, get comfortable. Let your eyes grow heavy. Let's begin. Most underground chambers begin with water finding a weakness in rock. Rain falls on the surface, moves through soil, and picks up a little carbon dioxide along the way. This makes the water mildly acidic, gentle enough to seem harmless, but strong enough to affect certain rocks over long periods. In limestone and other soluble stones, the water can slowly dissolve tiny amounts of mineral as it passes through cracks. At first, the opening may be almost invisible. With enough time, water follows the same route again and again, widening it into a passage. A cave is therefore not usually a sudden empty place. It is the patient result of water, rock, gravity, and time working together in darkness. Limestone is especially important in the world of caves because it is made mostly of calcium carbonate. This mineral reacts with weak natural acids in groundwater more easily than many harder rocks do. The change is usually slow, so the stone does not simply melt away like sugar in tea. Instead, water removes tiny amounts and carries them onward as in solution. Over thousands or millions of years, small paths can become conduits, then rooms, then connected systems. Landscapes rich in limestone often develop karst features, including sinkholes, disappearing streams, underground rivers, and springs. From above, such land may look like ordinary fields, hills, or woods. Beneath it, water may be moving through a hidden network of stone corridors. A simple crack can decide where a whole passage begins. Rock layers are rarely perfect blocks without weakness. They contain joints, bedding planes, faults, and old stress lines from lifting, cooling, folding, or pressure. Once water enters one of these openings, it has an easier path than it would through solid stone. Over time, the chosen crack may grow wider, while nearby cracks remain small. This is why many cave passages follow long straight lines, sharp bends, or flat layers that match the structure of the rock around them. The cave is not separate from the hill or plateau above it. It is an inner expression of the same old forces that shaped the ground before the passage ever opened. Ancient water levels can still be read in the shape of a passage. When a cave passage is fully filled with groundwater, water can dissolve rock on all sides, often creating rounded tubes or smooth walls. Later, if the water table drops, a stream may cut downward through the floor of the older tunnel. This can leave a narrow trench inside a broader passage, showing that the cave has lived through more than one stage. Rounded ceilings, old shelves, grooves, and canyon-like cuts all help scientists understand how water once moved. A dry chamber may seem still today, but its shape can remember a time when water filled it completely. The cave becomes a quiet diagram of older drainage and changing landscapes. Below the water table, passages form in a zone called phreatic. Here, openings are completely filled with water, so dissolution can happen in many directions at once. Gravity still matters to the wider system, but the passage itself may not look like an open stream channel. It can become rounded, tube-like, or maze-like. following cracks and bedding planes through the rock. If the water table later falls, that once flooded route may become an air-filled cave. Walking through it, a person may be moving through a former underwater space. The walls can still carry the memory of that stage, even after the water has shifted elsewhere. What feels like empty air may once have been a slow, mineral-rich flow. Above the water table, a different style of passage can develop. In this vadose zone, streams move through open air and follow gravity along the cave floor. Instead of dissolving evenly on all sides, the water cuts downward, forming trenches, small canyons, plunge pools and winding channels. A cave may preserve both stages at once, an older rounded tube from flooded conditions and a younger stream-cut groove below it. This layered shape tells a story of falling water tables, changing valleys, or shifting underground drainage. The passage is not only a route through stone, it is a record of where the water once was, where it went later, and how the cave adjusted to each new level. Hidden rivers continue shaping many caves long after the first openings form. A stream may disappear from the surface through a sinkhole, travel beneath fields or forests, and return later at a spring. Underground, it can carry sand, gravel, silt, wood, and dissolved minerals. In ordinary flow, it may quietly polish the floor. During floods, it can rise with surprising force, filling passages that seem dry most of the year. Mud lines, stranded leaves, rounded pebbles, and scalloped walls can all reveal these hidden movements. An underground river is not separate from the surface world. It is rain and runoff taking a darker route, turning the cave into part of a larger water system. Springs are often the places where cave water comes back to daylight. After moving through cracks, conduits, and chambers, groundwater may emerge at the base of a hill, beside a river, from a cliff, or through the floor of a valley. The water may look clear because it has passed through rock, but clear water is not always safe to drink. Its chemistry depends on the stone it touched and the materials it met along its underground path. Large karst springs can drain wide areas, linking distant sinkholes, sinking streams, and cave passages into one system. A spring may look peaceful at the surface, but it can be the visible end of a long, hidden journey. Sinkholes show that the surface and the underground are closely connected. In karst regions, water may dissolve rock below the ground until the surface slowly sags or suddenly collapses. Some sinkholes form gentle bowls, while others create steep openings where a roof has failed. They may collect rain, swallow streams, or reveal a way into deeper passages. A sinkhole does not always mean there is a giant open cavern directly below it. Sometimes it is only a sign that support has weakened or that water has been removing material in hidden spaces. Even so, the shape is a clue. It tells us that the land is not solid in a simple way, but crossed by slow underground change. Disappearing streams are not truly lost. In karst landscapes, a creek can flow across open ground and then vanish into a crack, sinkhole, or swallow hole. Downstream, the surface channel may become dry, while the same water continues below through conduits and cave passages. It may emerge far away at a spring, sometimes on the other side of a ridge. This makes karst drainage difficult to understand from the surface alone. Water does not always obey the visible valleys. It may follow a private map inside the rock. Anything carried by the stream can enter that hidden system too, which is why pollution in karst areas can move quickly underground. Karst aquifers can store and move groundwater through widened cracks and cave passages. In ordinary porous sediments, water often seeps slowly between grains. In karst, it can sometimes move much faster through channels and conduits. This makes springs respond quickly after rainfall, but it can also make groundwater more vulnerable. Pollutants entering sinkholes, losing streams, or thin soils may travel with less filtering than people expect. Many communities depend on karst water for drinking, farming, and industry. So understanding these systems is not only scientific, it is practical. A cave may look like a hidden natural wonder, but it can also be part of a living water supply, quietly connecting roads, fields, forests, and homes above. Scallops on cave walls are small records of flowing water. These shallow, spoon-shaped hollows form when moving water dissolves or erodes rock unevenly. Their shape reflects tiny swirls in the current. In general, smaller scallops suggest faster flow, while larger ones often point to slower movement, though each setting must be read carefully. Their orientation can help researchers infer which way water once traveled, even in a passage that is dry today. A wall covered with scallops may look like a pattern of scales or overlapping shells. It is really a stone memory of movement, left behind after the stream changed course or the water table fell. Stalactites grow downward from ceilings where mineral-rich drops hang in place. Water seeping through limestone can carry dissolved calcium carbonate into the cave. When a drop reaches the air, a little carbon dioxide may escape, and calcite can begin to crystallize. Most of the water falls away, but a tiny ring or layer of mineral remains. Repeated drop after repeated drop slowly builds a hanging form. Some stalactites are thick and blunt, while others are long and delicate. Their growth depends on water supply, temperature, airflow, and chemistry. They are not made quickly. Their beauty comes from thousands of quiet repetitions, each one leaving behind almost nothing, until the ceiling has written downward in stone. From the floor, stalagmites rise where drops land again and again. The falling water may still carry dissolved minerals after leaving a ceiling crack or stalactite. When it hits the floor, a small amount of calcite can settle at the landing spot. Over time, that spot becomes a low mound, then a rounded cone, and sometimes a tall formation. Stalagmites are often wider than stalactites because falling drops spread slightly on impact. Their layers can preserve clues about drip rate, water chemistry, and past climate above the cave. A stalagmite is a slow tower made by falling water. Its shape marks a place where the cave has been touched again and again by the same patient rhythm. When ceiling and floor formations meet, they create a column. A stalactite may grow downward, while a stalagmite rises below it. If the drip continues in the same place for a very long time, the gap between them can close. After contact, more mineral may build around the join, making the column thicker and smoother. It may look like a support holding up the roof, but that is not usually why it formed. The column exists because water followed one steady route long enough to connect two surfaces. Some columns are slender and graceful, while others are broad and ribbed. They make time visible in the vertical space between ceiling and floor. Flowstone appears where water spreads as a thin sheet instead of falling from a single point. It can coat walls, slopes, ledges, and floors with smooth layers of calcite. The result may look like frozen waves, pale curtains, or a stone waterfall. Impurities such as iron can add warm colors, including cream, amber, orange, brown, or red. Flowstone often covers rough older rock with a glossy skin, softening the shape of the chamber. Although it looks still, It records many visits from moving water. Each layer marks a time when water passed over the surface, lost carbon dioxide, and left a little mineral behind. Soda straws are among the most delicate cave formations. They are thin, hollow tubes that grow from the ceiling, often as early stages of stalactites. A drop of water hangs at the end, depositing calcite around its edge, while the center stays open. Water continues to pass through the tiny tube and reaches the growing tip. If the central channel becomes blocked, water may run down the outside and the straw can thicken into a more ordinary stalactite. Because their walls are very thin, soda straws can break from a careless touch or vibration. They show how precise cave growth can be when water, air, and mineral supply remain steady. Mineral-rich pools can create small rounded objects called cave pearls. A pearl begins with a grain of sand, a rock chip, or a tiny piece of older calcite. Gentle water movement rolls or washes over the grain, allowing mineral layers to coat it from many sides. Over time, it can become smooth and round like a quiet stone bead. Unlike pearls from oysters, cave pearls are not made by animals. They are geological, shaped by water chemistry and motion. They need just enough movement to coat them evenly, but not so much that they are carried away. In a shallow cave pool, stillness and motion meet in a small polished form. Helictites seem to grow against ordinary expectation. Instead of hanging straight down, they twist sideways, curl upward, or branch in tiny loops. They are usually made of calcite or aragonite, and their shapes may be influenced by capillary action, crystal structure, air currents, pressure differences, or microscopic paths inside the mineral. Gravity still exists, but the water involved is so small and carefully guided that the result can look almost weightless. Many helictites are extremely fragile. Their strange forms remind us that cave minerals are not limited to simple drops and cones. In the quiet air, tiny flows can ride sideways, making stone look as if it has learned to wander. Limestone dams build natural terraces around pools. When mineral-rich water flows slowly across a cave floor, calcite may deposit along the edge, where water meets air and stone. Over time, these mineral lips can grow into low walls, holding back shallow pools like steps on a slope. The water behind them may be clear and still, reflecting the ceiling in dark, glassy surfaces. Each rim can record a repeated water level or a stable path of flow. The dams are not built by sudden force. They are made by quiet deposition returning to the same boundary. A thin line of water becomes a lasting shape. Gypsum adds a different kind of brightness to some caves. Unlike calcite, gypsum contains calcium sulfate. It can form where sulfate-rich water reacts with limestone, or where evaporation leaves minerals behind. In dry cave sections, gypsum may appear as pale crusts, powdery coatings, needles, flowers, or sparkling crystals. These formations are often soft and easily damaged. Some look feathery, as if the stone has bloomed lightly from the wall. Gypsum can tell scientists about cave chemistry, airflow, moisture, and past conditions. It also shows that caves are not only places of dripping calcite. Different waters and gases can create different underground mineral worlds. Moon milk is a soft white cave material with an unusual texture. It may appear as paste, powder, or a damp, creamy layer on walls and formations. The name comes from its pale color, not from any connection to the moon. Many examples contain tiny calcite crystals and water, though the exact mineral content can vary. Microbes may play a role in some deposits, but moon milk does not form in just one simple way. Because it can be soft and fragile, a touch can mark or remove it. Moon milk reminds us that cave minerals do not always become hard, glossy shapes. Sometimes they form a quiet white skin where water, minerals, and tiny life meet. Popcorn-like knobs can cover walls, floors, and older formations. This cave popcorn is usually made of calcite or aragonite and grows where water seeps, splashes, or evaporates from a surface. Instead of forming a long dripstone or a smooth sheet, minerals gather in clustered bumps. Air movement and repeated wetting can influence the texture. Some patches are rough and sparkling, while others are rounded and soft-looking. Cave popcorn is common in many caves, but each patch reflects local moisture and airflow. It turns a plain surface into a miniature landscape of mineral beads, showing that small repeated changes can create rich texture. Aragonite crystals can grow as needles, sprays, or delicate clusters. Aragonite and calcite are made of the same chemical ingredients, but their crystal structures are different. That internal difference changes the shapes they tend to build. In caves, aragonite may form slender branching patterns, frost-like sprays, or pale needles on walls and ceilings. Water chemistry, magnesium content, temperature, and evaporation can all affect where it appears. Under some conditions, aragonite may later change into calcite, because calcite is usually more stable near ordinary surface conditions. These crystals show that the same basic material can become more than one kind of beauty underground. Draperies form when water runs along a sloping ceiling or wall edge. Instead of dropping straight from one point, the water follows a thin line and leaves calcite along its path. Over time, this creates a hanging sheet that may fold, wave, or ribbon like fabric. Thin draperies can be partly translucent when light shines through them, revealing bands of color from minerals and organic traces. They are sometimes called cave curtains because they look like stone cloth. Their curves are not random decorations. They record the exact paths of repeated water films, shaped by slope, gravity, and chemistry. A simple wet edge can slowly become a patterned mineral veil. Shield formations grow from narrow cracks under slight pressure. They often look like round or oval plates attached to cave walls, floors, or ceilings. Water moves through a thin central opening and deposits calcite on both sides, building matching plates outward over time. From the rim, stalactites or draperies may sometimes grow, making the shield look like a base for other formations. Their development can be complex, involving fractures, water pressure, and crystal growth. Unlike ordinary dripstone, a shield is not made mainly by water falling through open air. It is a reminder that hidden pressure inside stone can create broad, disc-like shapes in the cave. Boxwork looks like a honeycomb of thin mineral fins. It forms when cracks in the original rock are filled with a more resistant mineral, often calcite. Later, the surrounding rock dissolves or weathers away, leaving the filled cracks standing out from the surface. Wind Cave in South Dakota is especially known for this feature. Boxwork is different from stalactites and stalagmites because it is not mainly built into open air by dripping water. It begins inside the rock before the cave wall is exposed. When a passage opens around it, the mineral network remains. The result is a revealed structure, like a hidden pattern brought forward by loss. Still, cave pools can grow thin floating sheets of calcite called cave rafts. When carbon dioxide escapes from calm water, crystals may spread across the surface like a fragile mineral skin. Surface tension can hold the raft for a while. If disturbed, it may sink and collect on the pool floor, sometimes forming small stacks of flat pieces. Rafts only form where the water is quiet enough for the crystals to survive. They are delicate records of stillness at the boundary between air and water. In a cave pool, even the surface can become a place where stone briefly appears, floats, and then settles into darkness. Frostwork is not made of frozen water, despite its name. It consists of tiny branching crystals, often calcite or aragonite, that resemble white needles or frost. These crystals may grow in dry or airy cave sections where evaporation helps concentrate mineral solutions. They can spread across older formations, walls, or ceilings in fine sparkling clusters. Because the branches are thin, they are easily damaged by touch or careless movement. Frostwork shows how delicate cave growth can be when just a little moisture, the right chemistry, and moving air work together. It is stone arranged with surprising fineness, like a miniature winter that never needed ice. Anthodites look like mineral flowers blooming from cave walls. They are commonly made of aragonite needles that radiate outward from a central point. The name itself means flower-like, and the comparison is easy to understand, though the formation is entirely geological. Anthodites may grow where water seeps slowly and evaporates, leaving crystals to extend into open air. Humidity, airflow, chemistry, and crystal structure all influence their shape. They are not among the most common cave formations, which makes them especially valuable where they occur. In a place without sunlight or leaves, stone can still arrange itself into forms that feel almost botanical. Rounded underwater deposits called cave clouds can grow in pools. Unlike stalactites or stalagmites, they form below the water surface, where minerals coat submerged ledges, floors, or older formations. Their bulbous shapes reflect slow deposition in stable water. If the pool later drains or the water level falls, cave clouds may be exposed, revealing smooth, swelling forms that once grew underwater. They tell scientists that water stood in that place long enough for minerals to collect. A cave cloud is not a cloud at all, but a memory of a former pool. It is stone shaped in still water, then left behind when the underground environment changed. Mineral crusts can hide earlier stages of a cave's life. As calcite, gypsum, or other minerals deposit, they may seal older rock surfaces, sediments, fossils, or previous formations beneath a younger layer. This can protect what lies below, but it can also make the record harder to see. A wall may contain an old solution surface, then mud, then flowstone, each layer belonging to a different time. Scientists sometimes study natural breaks or exposed edges to understand this sequence. The surface visible today may not be the first surface of the cave. It may be the latest skin over a much older underground story. Different minerals give cave formations their colors. Pure calcite may appear white, clear, or pale cream, but cave water often carries traces from soil and rock above. Iron can add yellow, orange, red, or brown tones. Manganese may create grey or black markings. Organic material can warm the color of a formation. Bands may show that water chemistry changed over time. The colors do not always reveal a simple recipe, because crystal structure, light, moisture, and surface texture all matter. Still, every shade hints at what the water touched before it entered the chamber. A cave's palette is made from small traces carried through darkness. Sediments on cave floors can preserve floods, old soils, and surface change, Sand, clay, silt, gravel, leaves, and organic fragments may be carried underground by streams or washed through entrances during storms. When the water slows, these materials settle in layers. Fine clay can suggest calm water, while rounded gravel points to stronger flow. Over time, stacks of sediment may record repeated events, even after the cave becomes quiet again. Sediment can also protect bones, charcoal, pollen, or artifacts in the right conditions. The floor is therefore not just a place to walk. It can be a slow archive of vanished storms, old landscapes, and water that once moved through the dark. Breakdown piles form when pieces of ceiling or wall fall to the floor. Underground rock may look permanent, but caves adjust over time. Fractures widen, support changes, and weathering weakens surfaces. Blocks can detach and gather below as angular slopes. In many caves, these piles are ancient and stable, partly covered by sediment or later mineral growth. In others, fresh rockfall may expose lighter surfaces where the stone recently broke. Breakdown can enlarge a chamber, block a route, or create new spaces between fallen blocks. It is not only destruction, it is one way a cave finds a shape it can support, with gravity slowly joining water as a sculptor. Large chambers usually form through more than one process. A room may begin where fractures meet, where rock dissolves more easily, or where a stream carries material away. As space grows, the ceiling may shed blocks, and later mineral deposits may decorate the walls and floor. The final chamber can feel cathedral-like because humans compare it to built spaces, but it was not designed. Its size reflects rock strength, water chemistry, fractures, sediment movement, and collapse over long periods. A vast underground room is a natural volume slowly opened inside stone. Its stillness is the result of many small changes that made space for air. Sea caves form where waves attack weak places in coastal cliffs. The ocean does not usually dissolve sea caves in the same way that carbonic acid dissolves limestone inland. Instead, waves push water, air, sand, and pebbles into cracks, slowly widening them by physical force. Softer layers, faults, and joints can guide the shape. Some sea caves are short chambers, while others become tunnels that echo with moving water. Their floors change with tides and storms. They belong to the restless meeting line between land and sea, where every wave repeats a small act of pressure against the rock. Coastal arches can grow from the same wavework that makes sea caves. If waves cut into both sides of a headland, or if a cave breaks through to the other side, an arch may appear. Over time, the roof can weaken and collapse, leaving a sea stack isolated offshore. This sequence is not always simple or perfectly ordered, but it shows how cliffs change under repeated attack. A cave, an arch, and a stack may be different stages of erosion along the same coast. The island or headland may look solid from a distance, while the sea is quietly finding weaknesses at its edge. Lava tubes form when molten rock creates its own tunnel. During certain eruptions, the surface of a lava flow cools and hardens, while hotter lava keeps moving beneath it. If the liquid lava drains away, it can leave a hollow tube with walls, ceiling, and floor made from cooled volcanic rock. These caves can form much faster than limestone caves, sometimes during a single eruption. Their interiors may show ledges, smooth walls, lava drips, and marks from flowing molten material. A lava tube is not carved by ordinary water. It is the frozen root of fire, emptied after the eruption, and left as a dark passage through volcanic stone. Skylights in lava tubes appear when part of the roof collapses. From above, they may look like dark openings in a lava field, revealing a passage below. Sunlight can enter through the hole and create a sudden bright shaft inside the tunnel. In some places, plants grow where light and moisture gather beneath the opening. A skylight may also help scientists identify lava tubes on Earth and possible tube-like voids on other worlds. It is both an entrance and a window. The tunnel itself was made by flowing lava, but the skylight comes later, when gravity opens a section of the roof to the sky. Ice caves can mean two different things, and the distinction matters. Some are rock caves that contain ice because cold air becomes trapped inside. Others are caves formed within glaciers, where the walls are made of ice itself. In rock caves, winter air may sink into low chambers and remain there through warmer months. Water entering the cave can freeze into floors, columns, or clear layers. These features may grow and shrink with seasons and climate. The cave acts like a natural cold pocket, holding a piece of winter underground. Its frozen surfaces are beautiful, but sensitive to changes in airflow, temperature, and water supply. Glacier caves are passages inside moving ice. Meltwater, warm air, or flowing water beneath a glacier can open tunnels through the ice mass. Their blue color often comes from dense ice absorbing more red light and allowing blue light to travel farther. These caves can change quickly compared with stone caves. Passages may shift, collapse, or vanish as the glacier moves and melts. They are temporary features in a body that is itself slowly flowing. A glacier cave may feel like a frozen cathedral, but its walls are not still in the geological sense. They are part of moving ice, beautiful because they are brief. Sandstone caves often tell a story of grains and weak layers. Sandstone is made of sand-sized particles held together by natural cement. If the cement is weak, or if water, wind, frost, salt, and gravity act along certain layers, hollows can develop. Many sandstone caves are shallow shelters rather than deep branching systems, though some follow fractures or bedding planes farther into cliffs and slopes. Their walls may show cross-bedding, ripple marks, or color bands from the time when the sand was first laid down. A sandstone cave keeps the texture of ancient sand while becoming part of a rock shelter, cliff, or hillside. Salt caves are especially delicate because rock salt dissolves so easily. Water can remove salt much faster than it removes limestone, so these caves may change quickly by geological standards. They tend to occur in dry regions where salt deposits are protected from too much moisture, yet still touched by limited flow along cracks or layers. Their walls may be bright, translucent, banded, or unstable, depending on the structure of the salt. Because salt weakens and dissolves easily, these caves are sensitive to humidity and water. A salt cave shows how strongly rock type controls underground space. When the rock itself is easily carried away by water, the hollow becomes fragile. Marble caves form when water opens passages in marble, a metamorphic rock made from changed limestone. Heat and pressure transform the original limestone deep within the earth, but the rock can still contain calcium carbonate that weakly acidic water can dissolve. Marble passages may show smooth, pale walls, bands, folds, or colors inherited from the rock's earlier history. The same basic chemistry may be involved as in limestone caves, but the visual result can be different. A marble cave carries two long stories at once. First, the stone was changed by heat and pressure, and later water found its way through it, making quiet rooms inside altered rock. Hypergenic caves grow from water rising upward from deeper sources. In many familiar cave systems, rainwater enters from above and moves down through the landscape. Hypergenic caves can form differently. When deep groundwater rich in carbon dioxide, hydrogen sulfide, or other chemicals rises through fractures and dissolves rock from below. These systems may have maze-like patterns, cupolas, rising shafts, and unusual minerals. Their origins can be harder to read from the surface because the water source is not simply a sinking stream. They show that caves can form from below as well as above. Hidden circulation inside the earth can open rooms without ever beginning as ordinary surface runoff. Sulfuric acid can make cave formation more aggressive in certain settings. When hydrogen sulfide meets oxygen-rich water or air, chemical reactions and microbes may help produce sulfuric acid. This acid can dissolve limestone and create large chambers, unusual wall textures, and gypsum deposits. Carlsbad Caverns is one famous example where sulfuric acid speleogenesis helped shape major underground rooms. These caves are not made by fire, even though the chemistry can sound dramatic. They are formed through water, gas, microbes, and rock reacting in darkness. A sulfuric acid cave reminds us that tiny organisms and invisible gases can help create enormous spaces. Anchialine caves contain coastal underground waters linked to the sea. They are often found near limestone or volcanic islands and shorelines. Their waters may be layered, with fresher water above and saltier water below, depending on tides, rainfall, and hidden passages. Some specialized animals, especially small crustaceans, live in these unusual environments and may be found only in narrow regions. The connection to the ocean may be invisible, with tides gently raising and lowering water levels far from the beach. Such caves show that land and sea can meet underground, not only at the visible shore. A still pool may quietly breathe with the tide. Cenotes are natural openings where collapsed limestone exposes groundwater below. They are especially well known on Mexico's Yucatan Peninsula, where soluble rock and underground drainage have created many water-filled sinkholes. Some cenotes are open pools under the sky, while others are partly roofed chambers with clear water beneath formations. They can connect to large flooded cave systems that carry fresh water through the limestone toward the coast. For people and wildlife, cenotes have long been important water sources in areas with few surface rivers. A cenote is both a window and doorway, revealing the calm place where rainwater, collapse, rock, and underground flow meet. Blue holes are deep water-filled caves or sinkholes in marine or coastal settings. Some open directly into shallow seas, while others lie inland but connect to saltwater underground. Their dark blue appearance often comes from depth, clear water, and contrast with lighter surrounding sand or limestone. The water inside may be layered, with oxygen-rich water near the top and different chemical conditions below. Sediments in blue holes can sometimes preserve records of storms, sea level change, or environmental shifts. From above, a blue hole may look peaceful and still. Beneath the surface, it is a vertical cave system where depth, chemistry, and tides quietly matter. Deep cave air often stays close to the average yearly temperature outside. Rock buffers short-term weather, so daily heat and cold do not travel far underground. A cave may feel cool in summer and mild in winter, not because it makes its own weather, but because it is protected from quick changes. Airflow, water movement, entrance shape, and depth can all affect the exact temperature. Some passages breathe with pressure changes, while others remain nearly still. This stable environment helps preserve mineral formations and support specialized life. The calm of a cave begins with the simple fact that thick rock changes temperature slowly. Total darkness begins beyond the entrance zone. Near a cave mouth, daylight may support mosses, algae, ferns, or small plants if moisture is available. Farther in, light fades until photosynthesis can no longer support green life. Energy must then arrive in other ways: leaves washed in by water, roots entering cracks, guano from bats, dead insects, or chemical reactions in unusual systems. The deep zone is shaped by darkness, stable moisture, and limited food. It is not empty, but life there must use energy carefully. For human visitors, darkness changes perception. For cave animals, it changes the body itself over generations. Moisture shapes the underground atmosphere as much as darkness does. In many deep cave zones, humidity is high, sometimes near saturation. This slows evaporation from pools, water films, and mineral surfaces. It can help active formations continue growing because dripping water does not dry too quickly. Humidity also matters for cave animals, especially tiny invertebrates that lose moisture easily. Near entrances, dry outside air can create stronger seasonal changes, while deeper chambers remain more constant. A cave often feels still partly because moisture softens the air. Dampness is not just a feeling. It is part of the system that keeps minerals and life working underground. Air inside a cave can move in quiet pulses. Changes in outside temperature and pressure may push or pull air through entrances, cracks, or openings at different heights. When a cave has high and low entrances, colder or warmer air may move through it like a slow chimney. These movements can influence humidity, carbon dioxide levels, temperature, and mineral growth. Some caves feel almost still, while others have noticeable drafts. The air is not simply trapped forever. It exchanges with the surface according to cave shape, weather, and hidden cracks. A cave breathes slowly, often too gently for a visitor to notice. Carbon dioxide levels can vary from one cave to another. Soil above a cave often contains extra carbon dioxide because roots and microbes release it while breaking down organic matter. Water carrying this gas can help dissolve limestone. Inside the cave, carbon dioxide may collect in low or poorly ventilated areas, and visitors or animals can add small amounts through breathing. Higher carbon dioxide can influence how calcite dissolves or deposits. It also matters for comfort and safety in some settings. Cave air has its own chemistry, shaped by the living surface above, the shape of the passages, and the slow exchange of air through hidden openings. The entrance zone is a gradual border, not a sharp line. Sunlight, wind, leaves, soil, insects, and seasonal temperature changes reach this area more easily than the deep cave. Mosses or ferns may grow near the mouth, animals may shelter in cracks, and organic material may gather on the floor. Farther inside, light fades, daily weather softens, and the community changes. This transition zone can be one of the most active biological parts of a cave because it links the surface with the dark interior. It is a threshold where two worlds overlap for a short distance. Roots can bring sunlight's energy into a place without light. In some regions, tree roots grow down through cracks in search of moisture and eventually reach cave air. They may hang from ceilings like pale threads or woody cords. Insects, microbes, and other small organisms can feed on or shelter around them. Roots may also guide dripping water or trap fine sediment. Their presence shows that a cave is not sealed from the forest, grassland, or soil above. A root hanging in darkness is the surface reaching downward, carrying the work of leaves into a chamber where no leaf can grow. Troglobites are animals adapted to spend their whole lives in caves. Many have pale bodies, reduced eyes, long antennae, or sensitive touch. These traits are not choices made by individual animals. They develop over generations as cave conditions favor certain inherited features. Troglobites may include fish, salamanders, spiders, insects, shrimp, and other invertebrates, depending on the region. Their world is often low in food, so they may move slowly and use energy carefully. Outside the cave, light, heat, and dryness can be harmful. A troglobite shows how deeply a place can shape a body. In darkness, evolution often favors patience and sensitivity. Blind cave fish are famous examples of life shaped by darkness. In some species, eyes are reduced or covered by skin, while other senses become more useful. A fish may detect water movement, touch, smell, or tiny vibrations. Pale color is common because pigment offers little benefit where sunlight never reaches. These features are inherited adaptations, not damage that happens to a single fish during its life. Many cave fish live in limited water systems and may be found only in one cave or aquifer. That makes them vulnerable to pollution, lowered water levels, or habitat change. Their quiet lives carry the shape of their hidden world. Bats use many caves as roosts, nurseries, or seasonal shelters. A cave can offer darkness, stable temperature, and protection from harsh weather. Some bat species gather in large colonies, while others use caves in smaller groups or only at certain times of year. They usually leave to feed outside, then return carrying surface energy back underground. Their droppings, called guano, can support insects, fungi, bacteria, and other tiny cave life. Not every cave has bats, and not every bat depends on caves, but the connection is important in many landscapes. Disturbance during winter rest or breeding seasons can harm sensitive colonies. Guano can become the center of a cave food web. In dark places where little plant material enters, droppings from bats, birds, or other animals bring nutrients from the outside world. Fungi and bacteria break the material down. Small invertebrates feed on the guano or on the microbes growing in it. Predators then feed on those smaller creatures. A pile of guano may look simple, but it can store enough surface energy to support a whole local community. It may also affect the chemistry of cave floors and nearby minerals. In the dark, even modest nutrients can decide where life gathers. Microbes live on cave rock, sediment, water films, and mineral surfaces. These bacteria, archaea, and fungi are often too small to notice, yet they can shape underground ecosystems. Some feed on organic matter washed in from outside. Others use chemical reactions involving sulfur, iron, methane, or hydrogen. In certain caves, microbial communities form soft mats, thin coatings, or delicate patterns on walls. They can influence mineral deposition, rock weathering, and water chemistry. Their presence shows that a cave is not simply stone and empty air. Much of its living activity is hidden at a scale too small for ordinary sight. Chemoautotrophic microbes can support life without sunlight in some caves. Most familiar food chains begin with plants or algae using solar energy. In certain underground systems, microbes use chemical energy instead, involving substances such as sulfur, iron, methane, or hydrogen. These microbes may become the base of unusual food webs, supporting other microscopic life and small animals. Such systems are not found in every cave, but where they occur, they change how we imagine darkness. The first step of the food chain does not always need daylight. In some hidden places, it begins with chemistry rising from water, gas, or rock. Crickets often travel between cave darkness and the surface. Many shelter in cave entrances or deeper damp areas during the day, then leave at night to feed outside. When they return, their droppings, eggs, bodies, and movements carry surface nutrients into the cave. This can support spiders, beetles, mites, microbes, and other small life. Cave crickets are not always full-time cave specialists, but they can be important in food-poor underground habitats. Their long legs and antennae help them move through darkness. They are small nightly messengers between two worlds, the open air where they feed and the stone shelter where they rest. Salamanders may use caves without becoming permanent cave dwellers. Some species shelter in entrances, damp cracks, or twilight zones where moisture is high and temperature is stable. They may feed on small invertebrates and move in or out depending on season, life stage, and local conditions. True cave-adapted salamanders can have reduced eyes or pale bodies, but many cave-using species still resemble surface animals. This distinction matters. Not every creature found underground belongs completely to the dark. Some are visitors, some are regular guests, and some are deeply adapted residents. A salamander on a damp cave wall shows the cave as refuge. Specialized beetles can evolve in isolated cave habitats. In darkness, many cave beetles have reduced eyes, pale bodies, long legs, and sensitive antennae. Their shapes help them search slowly through cracks, sediments, and guano deposits where food may be scarce. Some species are known from only one cave or one small region, because underground populations can become isolated for long periods. That makes them scientifically valuable and vulnerable. Changes in moisture, food supply, pollution, or human disturbance can affect a population with nowhere else to go. A tiny beetle may carry a deep evolutionary story in its body. Mammoth Cave in Kentucky is famous for its enormous connected system of passages. It formed in layers of limestone beneath a karst landscape of ridges, valleys, and sinking streams. Some passages are broad, dry, and tunnel-like, shaped by ancient water flow. Others connect to active underground waterways. The cave also has a long human history, including indigenous use, saltpeter mining, tourism, and scientific study. Its size helps scientists understand how cave systems grow across long distances and through many levels. Mammoth Cave reminds us that a cave can be more than one chamber. It can be a hidden geography beneath familiar ground. Carlsbad Caverns in New Mexico shows how deep chemistry can create vast rooms. Hydrogen sulfide and oxygen helped produce sulfuric acid that dissolved limestone from below, opening large spaces over long periods. Later, mineral-rich water decorated many areas with stalactites, stalagmites, columns, draperies, and other formations. The famous large chamber gives a sense of hidden scale beneath a dry surface. Carlsbad also connects to life above through bat flights from its natural entrance during warmer seasons. It is a calm example of how a desert landscape can conceal enormous stone rooms, shaped by invisible chemical processes and later softened by mineral detail. Waitomo's glowworm caves in New Zealand are known for living lights in darkness. The glow comes from larvae of a fungus gnat, not from ordinary earthworms. These larvae produce blue-green bioluminescence and hang sticky silk threads to catch small flying insects. In cave darkness, their lights can look like a quiet star field across the ceiling. The glow is not decoration. It is a hunting tool. The cave provides darkness, moisture, and sheltered air, while flowing water and insects help support the life cycle. The scene feels magical, but its explanation is biological and practical. Lechuguilla Cave is valued for its rich and fragile mineral formations. Located in New Mexico, it became widely known to science after access to extensive passages opened in the 1980s. The cave contains gypsum chandeliers, aragonite crystals, sulfur-related minerals, and other unusual deposits. It is not managed for ordinary tourism because its formations are delicate and its scientific value is high. Lechuguilla connects to the wider story of caves, shaped partly by rising chemically active waters. Its rooms show that underground beauty is more varied than the familiar image of stalactites and stalagmites alone. It is a mineral laboratory held quietly inside rock. Son Doong Cave in Vietnam is known for its enormous scale. Formed in limestone, it carries an underground river through a vast system in Phong Nha Ke Bang National Park. In places where the roof has collapsed, sunlight enters through openings called dolines, allowing plants to grow far below the surface. Mist, dripping water, high walls, and giant passages can make parts of the cave feel like a hidden valley inside the earth. The processes behind it are familiar: soluble rock, powerful water flow, collapse, and long time. The result is extraordinary because the cave contains not only rooms, but a sense of landscape. Sediments and formations can preserve ancient climate records. Stalagmites are especially useful because they grow layer by layer from dripping water and can remain in place for long periods. As each layer forms, it may trap chemical clues from rain, soil, vegetation, and temperature conditions above the cave. Scientists study oxygen and carbon isotopes, trace elements, and growth bands to learn about wetter or drier times in the past. Dating methods such as uranium-thorium dating can place some calcite layers in time. The record is complex and local, but a careful stalagmite study can turn a dark formation into a quiet climate archive. Pollen grains can enter caves and survive under the right conditions. They may arrive through wind, water, animals, or sediment washed from the surface. Because pollen grains have durable outer walls, they can remain preserved in cave deposits for long periods. Scientists can study them to learn what plants once grew above or near the cave. Changes in pollen types through layers may reveal shifts in climate, vegetation, or land use. The evidence is tiny, often invisible without a microscope, yet it can describe whole landscapes. A dark cave floor may hold traces of forests, grasslands, or shrubs that once flowered in the light. Packrat middens can preserve plant material for thousands of years in dry cave entrances and rock shelters. Packrats gather leaves, seeds, twigs, and other objects into nests. Their urine can crystallize and harden the material into a protective mass. In dry conditions, these middens may preserve ancient plant remains remarkably well. By identifying the species inside them, scientists can reconstruct past vegetation and climate near the cave. The midden was not made as an archive. It became one through shelter and dryness. A small animal's nest can become a sample of an older landscape, stored quietly near the edge of darkness. Animal bones may enter caves in many ways. Animals can live there, fall into shafts, be carried in by water, or be brought by predators. Some caves act as natural traps, when steep openings or sinkholes are hidden by vegetation, snow, or darkness. Over time, bones from many animals may collect in one place. Scientists study their position, age, and condition to understand how they arrived. The story of the deposit matters as much as the bones themselves. A cave can preserve evidence of extinct animals and past environments because it protects remains from sunlight, rain, and surface erosion. Footprints in cave clay can preserve brief movements with surprising clarity. A person or animal may step across soft mud, leaving impressions that later harden or remain protected from weather. In the open air, such tracks would usually vanish quickly. Underground, they may survive for thousands of years if the floor is not disturbed. A trackway can show direction, pace, size, and sometimes group movement. It is different from a tool or bone because it records a moment of motion. A footprint is a small event held in stillness. It can make the past feel close because it preserves where a living body once crossed the cave floor. Charcoal and soot can reveal ancient fire use inside caves. People may have carried torches, built small fires, or used lamps while moving through dark passages. Smoke marks on ceilings, charcoal fragments, and burned material in sediment can help archaeologists understand how people lit, entered, or used underground spaces. These traces must be interpreted carefully because natural fires near entrances or later disturbance can complicate the record. Still, in the right context, fire evidence can show human presence in a place where light had to be brought deliberately. A soot mark on stone is a shadow of old flame, left behind after the fire itself disappeared. Ancient cave art survives because underground walls are protected from ordinary weather. In several parts of the world, people painted, drew, engraved, or marked cave surfaces thousands of years ago. Images may include animals, signs, hand shapes, and patterns, though each site has its own meaning and history. Stable temperature, darkness, and shelter from rain can help preserve art far longer than exposed rock. Even so, these places remain fragile. Changes in humidity, carbon dioxide, microbes, lighting, or human contact can damage them. A decorated cave is not simply a gallery. It is a protected interior where human attention once met stone, shadow, and memory. Pigments used in cave art often came from minerals that could last. Red and yellow ochres contain iron oxides, while black may come from charcoal or manganese minerals. Artists mixed, ground, applied, or engraved materials in ways that varied by place and culture. The survival of a pigment depends on the wall surface, moisture, chemistry, and later disturbance. Some images remain vivid, while others are faint traces. The mineral nature of many pigments help them endure in sheltered settings. A painted line underground can outlast the person who made it by many thousands of years, turning color into one of the cave's quiet records. For people, cave entrances have often served as shelters without complete separation from daylight. People could use the mouth of a cave or rock shelter for protection from wind, rain, sun, or snow while still remaining near the outside world. These spaces may contain hearths, tools, bones, shells, charcoal, or other traces of daily life. Deeper chambers sometimes had special uses, But many practical activities took place near entrances where light and fresh air were available. The entrance was a useful middle ground. It offered shelter without the full darkness of the inner cave. For human history, this threshold can be as important as the deep rooms beyond. Maps turn exploration into shared knowledge. Cave survey teams measure distances, directions, slopes, passage shapes, entrances, water routes, and important features. Modern tools may include laser distance meters, digital compasses, and software. But the work still depends on patience underground. A map must turn winding three-dimensional passages into something others can understand. It can guide science, rescue, conservation, and future exploration. Without mapping, a discovery may remain only a memory held by a few people. With mapping, the cave becomes part of a larger record. Each line represents real space hidden inside the earth. Acoustics underground depend on chamber size, wall texture, and passage geometry. A small, rough tunnel may absorb sound quickly, while a large, smooth room can return long echoes. Curving passages can carry voices in unexpected ways, making a sound seem to come from somewhere else. Drips, streams, and moving air add their own quiet layers. Ancient people may have noticed these effects in some decorated caves, though each site needs careful study. For modern explorers, sound can hint at nearby space when light is limited. A cave has no designed acoustics, but its stone surfaces give darkness a voice. Show cave paths are designed to protect visitors and the cave environment. Walkways guide people through safer routes, while keeping feet away from delicate floors, pools, sediments, and formations. Railings reduce accidental touching, and planned lighting allows people to see without illuminating every surface all the time. A well-managed route concentrates human impact in a limited area, rather than spreading it through the whole cave. The path may look like a convenience, but it is also a conservation tool. It creates a narrow human line through a much larger natural system that must remain mostly undisturbed. Artificial lighting can change a show cave. Where electric lights stay on near damp surfaces, algae, mosses, or cyanobacteria may grow in places that would naturally remain dark. This growth is often called lamp flora. It can alter the look of walls and formations and may affect delicate surfaces. Cave managers can reduce the problem by controlling light strength, limiting how long lights stay on, choosing suitable wavelengths, and cleaning carefully when needed. Show caves let many people experience underground beauty, but they also require thoughtful care. A developed cave is both a natural place and a managed space. Touching formations can damage processes that took centuries to create. Human skin carries oils, dirt, and tiny particles that may coat mineral surfaces. Even a light touch can leave a film where future calcite does not attach in the usual way. Delicate formations such as soda straws, helictites, and crystal edges can also break under small pressure. Damage that happens in a second may remove growth that took a very long time. This is why protected caves ask visitors to stay on paths and keep hands away from walls. The rule is not only about appearance. It protects slow growth that may still be active. Gates can protect sensitive cave entrances when they are designed carefully. A good gate is not just a barrier. It must consider airflow, bat movement, floodwater, temperature, and the needs of the cave ecosystem. Poorly designed gates can change ventilation or block animals that depend on the entrance. Bat-friendly designs use spacing and placement that allow bats to pass while limiting human disturbance. Gates may protect rare species, archaeological remains, fragile formations, or dangerous passages. The goal is not to hide caves from curiosity. It is to let them keep breathing while reducing harm. Conservation often begins above the cave, not at the entrance. Water enters underground through soil, cracks, sinkholes, and sinking streams. That means pollution, sediment, fertilizer, fuel, trash, and altered drainage on the surface can affect the cave below. A gate can protect an opening, but it cannot protect the water system by itself. Forests, fields, roads, and watersheds all matter. A clean drip inside a chamber may depend on healthy soil and careful land use overhead. Cave protection is not only about preserving beautiful formations. It is about understanding that the underground receives messages from the surface through every path water follows. Ethical caving follows a simple idea: leave the cave as unchanged as possible. Experienced cavers avoid touching formations, disturbing animals, leaving trash, marking walls, or taking souvenirs. They respect closures made for wildlife, archaeology, safety, or conservation. Even footprints can matter in soft sediment that has remained undisturbed for a very long time. The goal is not to remove wonder from exploration. It is to let wonder remain for the cave itself and for future visitors. A cave is not a place that can quickly repair every mark. Its slowness is part of its value. Rescue underground requires patience, mapping, and specialized skill. A simple injury can become difficult when passages are narrow, wet, vertical, or far from the entrance. Rescuers may need ropes, stretchers, diving equipment, special communication systems, and teams trained to move carefully through complex spaces. Good maps and survey points can save time by showing routes, climbs, water hazards, and tight sections. Prevention is always important, which is why experienced cavers plan trips, carry multiple lights, watch the weather, and tell others where they are going. Caves are beautiful, but not casual places. Their quietness asks for respect. Diving opens flooded passages beyond ordinary walking or climbing. In karst regions, large parts of a cave system may remain underwater, connecting springs, cenotes, sinkholes, and coastal outlets. Divers use specialized training and equipment because flooded caves are dark, complex, and unforgiving. Scientifically, cave diving can map hidden water routes, discover species, and gather information about geology and groundwater. The water may be clear enough to confuse distance, or cloudy if fine sediment is disturbed. A flooded cave is not an empty pool. It is a submerged landscape where ancient rock passages continue beyond the reach of air. Underground lakes reflect the level and movement of groundwater inside a cave. Some are still pools in quiet chambers, while others connect to flowing passages, springs, or flooded systems. Their surfaces may rise after rain and fall during dry periods. Clear water can make depth hard to judge, especially when the floor is pale or far below. Sediments, minerals, and tiny life may collect in or around the lake. A cave lake seems motionless at first glance, but it may be part of a wider hydrological system. It is the water table made visible in a dark room. Waterfalls can form where cave streams drop from one level to another. A passage may intersect a vertical shaft, a resistant rock layer, or an older route below. Water then falls through open air before continuing along the floor. Some underground waterfalls are small and quiet, while others roar during floods or wet seasons. Their spray can influence humidity, mineral deposition, and erosion nearby. They also revealed that caves are not always level tunnels. They can contain steps, pits, ledges, and stacked roots shaped by changing water tables. An underground waterfall is surface energy hidden in darkness, still obeying gravity far below the land. Stacked cave levels can record how valleys and water tables change through time. Older passages may sit high and dry above younger active streams. As rivers outside cut deeper into the landscape, underground drainage may also shift downward. A cave system can therefore develop several levels, each tied to a former stage of erosion and water flow. Walking from one level to another may feel like moving through different ages of the same cave. The upper roots are quiet memories, while lower passages may still carry water. Such systems show that caves grow with the landscape, not apart from it. Cupolas are rounded pockets in cave ceilings. They can form where water or gas dissolves rock upward, creating smooth domes or rising chambers. In some hypogenic caves, cupolas may be signs of upward-moving fluids or gases that once collected beneath a ceiling. Their shapes differ from ordinary dripstone because they are carved into the original rock rather than deposited on top of it. A cupola can look like a small dome in the darkness, quiet and empty. It is really a record of dissolution moving upward, showing that cave making can work from below as well as from streams flowing downward. Speleogens are cave features carved from the original rock. They include scallops, pockets, notches, channels, pendants, and other shapes made by dissolution or erosion. This makes them different from speleothems, which are deposits added later, such as stalactites or flowstone. Speleogens are part of the cave wall itself. They reveal how water, gas, or sediment once moved through the passage. A decorated cave may draw attention to the minerals that grew after the room opened, but the carved shapes beneath them can be just as important. They are the cave's original handwriting, cut into stone before the later mineral layers arrived. Travertine forms when mineral-rich cave water reaches the surface. At springs, carbon dioxide may escape from groundwater that has dissolved limestone. Calcite can then settle out, building pale crusts, terraces, dams, or rounded deposits in daylight. Travertine is related to the chemistry that forms many cave decorations, but it often grows outside or near entrances. Plants, algae, and flowing water can influence its texture. Some travertine terraces form stepped pools, while smaller deposits appear as rough coatings. The spring becomes a meeting place between underground and open air. Cave water continues its mineral work even after leaving darkness. In cold caves, ice can preserve layers like a frozen archive. In cold caves, water enters, freezes, and builds up over years or centuries. Dust, pollen, charcoal, or other tiny materials may become trapped inside. The layers can reflect changes in winter cold, summer melting, rainfall, or airflow, though each cave has its own local controls. Ice is often more vulnerable than stone because it responds quickly to warming or altered ventilation. When old ice melts, the record inside can be lost. A cave ice deposit is both beautiful and fragile, storing older seasons in clear or cloudy bands beneath the ground. Paleocast is ancient cast that was buried and preserved. Old caves, sinkholes, and dissolved rock surfaces can be filled with sediment or minerals, then covered by younger rocks over geological time. Later, erosion, quarrying, or scientific study may reveal them again. Paleocast can help geologists understand former landscapes, sea levels, climates, and groundwater systems. In some places, ancient cavities also influence where minerals, oil, gas, or groundwater collect. A paleokarst surface is a fossil landscape made of dissolved stone rather than bones. It shows that caves are not only forming now. The Earth also holds old underground worlds that were closed, filled, and kept inside younger layers. Speleology is the scientific study of caves and the systems connected to them. It can include geology, hydrology, biology, archaeology, climate science, mapping, and conservation. A speleologist may study how water moves through karst, how minerals grow, how animals adapt to darkness, or how ancient traces are preserved. Caves require careful work because many features are fragile and conditions can be dangerous. The science is not only about going underground, it is about understanding how the hidden world connects to the surface. A cave may feel separate, but speleology shows that it belongs to water, rock, air, life, and human history all at once. Other worlds may also contain caves. The Moon and Mars have volcanic landscapes where lava tubes are considered possible, based on surface features such as skylight-like openings and sinuous channels. These extraterrestrial caves have not been directly explored by people, but they are important in planetary science. A cave on the Moon or Mars could offer shelter from radiation, micrometeorites, and extreme temperature swings. Studying lava tubes on Earth helps scientists imagine what such spaces might be like elsewhere. The idea is quiet and wide at the same time. A hollow beneath a volcanic surface may matter not only on Earth, but on distant worlds too. These hidden places matter because they connect deep time, water, stone, life, and human memory in one underground world. A single cave may begin with fractures in ancient rock, grow through patient water movement, shelter unusual animals, collect sediments, and preserve signs of people who entered long ago. Its formations may still be growing drop by drop, while older passages sit dry above active streams. Its entrance may seem small compared with the system inside. Its quiet air may depend on weather, soil, and life far overhead. A cave is never only empty space. It is a meeting of many slow stories. These underground worlds leave a calm sense of how much the Earth can hold beyond ordinary sight. Beneath hills, forests, deserts, cliffs, and coasts, water has opened hidden paths through stone. Minerals have grown in patient layers. Living creatures have adapted to darkness. Human traces have sometimes remained where sunlight and rain could not easily reach them. A cave may seem still at first, but it is never meaningless. Its walls can remember old rivers, its floors can hold vanished climates, and its chambers can protect fragile signs of life and memory. Discovery does not always belong to bright open places. Sometimes knowledge waits in silence, in slow drips, pale crystals, cool air, and passages shaped long before anyone gave them a name. Caves are records of water, chemistry, gravity, shelter, and time, written in a language of stone. Their quietness is not emptiness. It is patience made visible. For now, let that hidden world remain quiet in the mind, deep beneath the surface, calm and enduring. Sleep well. Good night.